Hello everyone, today I'm going to talk about the bizarre extreme multi-wing flying machines built by Horatio Frederick Phillips, who was a very early airplane design pioneer. In fact, he didn't even call them airplanes yet, that name wasn't established yet. He was a more or less direct competitor to the Wright brothers in building the first powered or sustained powered flying machine. He was essentially the British side competitor to the Wright brothers. However, his airplane design was a lot more weird from today's perspective, because while he had a somewhat more modern control design with wings around the center of lift and a elevator and rudder at the tail of the airplane providing both stability and control, he did build multiplanes, and not just biplanes or triplanes, but 50 planes or 100 planes, which does make sense because he studied aerodynamics very thoroughly. However, aerodynamics at that time was mostly focusing on the geometry of a single wing because they didn't have the means to completely understand the flight dynamics of an overall airplane yet. So, looking at a single wing, it turns out that high aspect ratio wings are much more efficient than low aspect ratio wings. Now, what that means is that a wing with a long wingspan to depth ratio, or a very short wing in the direction of flight with a extreme wingspan, is a lot more efficient than a short or normal shaped wing. Now, this is very simplified and doesn't keep up as proportional as it does at high ratios. When you go to low ratios, you can see that in jet fighter wings, that wings with a low aspect ratio or short wings still produce some lift and can actually be pretty good, but it does boost the wing's efficiency if it has a very large wingspan, and you can see that when you look at efficient gliders. And at the time, low speed and high glide ratio wing design was what it was all about, because that was necessary to get airplanes flying at all. So while not quite as advanced, all airplanes from that time most directly compared to the gliders of today. High aspect ratio wings have a better glide ratio because they have less friction with their reduced depth, and their wingspan influences their lift coefficient. However, of course, the wingspan is very limited, especially at that time with those materials and those construction techniques. There was a limit to how large a wingspan an airplane could have, and so to reach a high aspect ratio, the wing depth would have to be reduced, which made for a very thin, very small wing profile, so a single wing simply was not enough to lift an airplane. It didn't have enough wing area. And so he stacked them over and over each other in a multiplane, which does have quite a few disadvantages and isn't really ideal, but even from today's perspective, it does have some advantages. It is a somewhat viable idea. Of course, at the time, the influence of wings over each other with turbulence was not quite as well understood, but the biggest issues were actually stability, both flight dynamically and structurally. Such low depth wings do get a little bit unstable because even a small amount of turbulence or a small amount of movement means a large movement compared to their depth, so a large change in angle of attack. Essentially, this is again vastly simplifying aerodynamics to make the relations between different dimensions more understandable, but the general concept holds true, and low depth wings do get very unstable. They also cause quite a bit of drag because in those multiplanes they were stacked closely over each other, still with enough distance to still produce a lift, but the air did gain pressure as it went through the slits between those wings, and thus the whole plane worked a little bit like a drag chute. Then there were also, of course, structural issues because a low depth wing itself isn't really a big structural problem, but he did also use relatively thin profiles, and of course that means that the thickness of the wing compared to the depth of the wing is relatively low, which together with the short depth of the wing means a very, very, very thin wing, which is, well, if you consider the wing as essentially a beam that holds the plane up, it gives you a very large leverage, and thus the wings tend to bend up a little bit like they were made out of paper. And these structural issues, of course, then again reduced his wingspan and thus made his multi-wing constructions even more extreme. It did kind of work out in the end. He did manage to get a machine actually flying a 200 winged multiplane. You can see it in the picture. They are stacked in two directions actually. There are four behind each other in these four clusters, which are each 50 wings high. Of course, he did understand that stacking wings behind each other isn't a really great idea because a lot of wake and turbulence and already downwashed air influences the wings behind a wing, and it essentially turns them into something similar to one lower aspect ratio wing, which is what he didn't want. But he left enough distance between them, and there was a limit to how high you could stack wings atop of each other. The overall idea didn't really compete with biplanes or later just simple monoplanes very well. While he did manage to get one flying, it wasn't the standard design that carried early flying machines and then was taken over by later flying machines. However, he did also contribute to wing profiles, which is a bit less spectacular, but he did a lot of scientific work researching and proving that bent wing profiles or curved wing profiles are a lot more efficient than flat wing profiles, which seems obvious from today's standpoint, but he also researched how exactly a wing was best bent and validated the from today's standpoint, classic wing design with a relatively strong leading edge that is slightly sloped downwards actually, and then the wing bends as it goes backwards, and then has a large trailing edge that is bent upwards. So he did pioneer the idea of not just starting with an angle of attack of 0 and then bending the wing back to gain the full angle of attack for more efficiency, but also bending the wing actually downwards at the start, which is still used in a slightly modified way in wing profiles today. Of course, today's wing profiles have a lot more thickness to them and aren't just bent sheet metals, but the idea still is used in airliner wings to this day, which was a much more lasting and, although less spectacular, a lot more interesting contribution to aviation. Although today, of course, we do see such extreme multi-plane lifting surfaces in a slightly different context, not as airplane wings, but as grid fins in the Falcon 9 rockets, where you have somewhat different design considerations. The purpose of a grid fin is different from that of an airplane wing. For example, the grid fin doesn't really have to be efficient as such. It doesn't have a strong lift to drag ratio because it's not gliding, and in fact it's helpful if it slows down the rocket. So the pressure build-up of the extreme multi-wing design isn't really a problem here. What's much more important is to keep each wing small so that the overall design is can be folded in and is relatively easy to turn around and control. Actually, the stability issues of the extreme multi-wing design is an advantage here too, and the exposed surface area is actually kept relatively small. So in this way, the multi-wing design somewhat still contributed to today's technology. So I hope you found this little excursus into weird historic flying machines and the design considerations that went into them at the time and why this design didn't really take over in today's time. Interesting. I'm always open for questions about aerospace engineering or aircraft or physics in general. And as always, thanks for watching.